So today we're going to get into simple pendula. Remember last time we talked about a spring, we hooked it up horizontally and it just oscillated back and forth, back and forth. Well, we're going to expand on this today. First thing we're going to do, we're going to make this twice as much fun. We're going to add two springs. Now if you look, as this box goes back and forth, delta x1 and delta x2 are going to be the same. So we'll combine these terms. This is exactly like we've been combining terms before. Again, always look for things that are similar. So what does this do? In an isolated system, dE dx1 is 0, and you get this expression for acceleration. Okay, this looks like our simple harmonic oscillator equation, except now omega effective is just omega of spring 1 squared plus omega of spring 2. And this whole top term becomes your effective spring constant. Just like the term in front of kinetic energy kind of became your mass effective, it's very similar. So we can model all these springs as one spring that is the effective oscillation of the system, or constant for oscillation of the system. Now let's take everything we've learned and turn it 90 degrees. So now our spring is going to oscillate up and down, which means we just add this mgy term from gravity. Again, we write the energy equation, same type of thing. We take the derivative with respect to position, and then we get our term for acceleration. And this is the only piece that is different, this little constant. So is that constant going to affect the oscillation? Well, the answer is no. All it does is change your equilibrium length. You still oscillate with omega. It only affects where the spring was squished. It just affects your initial squish of the spring. That's it. The oscillation around your new equilibrium point, this LE, L effective, doesn't change. The system always oscillates. Same way, just new equilibrium point. That's what LE is actually, L equilibrium. Now let's take a look at what most of us think of when we start thinking of pendulum. Ball on a string. So here's the ball, it's going to trace out this circular path. And notice if it traces out this circular path, that's why we're going to use this I omega squared. It looks like rotational motion, except your potential energy term comes from gravity. All right, so what's this change? Well, this is L cosine theta. We're using cosine because it's this piece right here. And it's minus because of how I set up my axis. Again, always be careful of how you set up your axes. MLA, MG, so this just same type of thing. L comes out because this is the I for a point particle. And then alpha being your angular frequency, MGL sine theta. And their plus goes away. Or you get a plus, sorry. So now what we're going to get is this alpha is equal to minus GL sine theta. That's a little bit messy. Let's see what we can do with this. Well, we can Taylor series. So if we use the Taylor series, if we say small oscillations, you can get rid of all these other terms. So that's what we're going to do. For small angles, this just becomes minus G over L theta, which is exactly, if this becomes theta, and this is d theta squared, it looks exactly like a spring, where your angular frequency is given by the square root of G over L, just like before. And that's a pretty good result. Kick it up one more notch. Let's add a drag term. All right, so this would just be energy loss to the system. That's all we've talked about. Friction, air resistance, just take energy out of the system. And this is a common one that depends on velocity. Start in the exact same place. We write our energy equation for our spring. Except now on this side, we get this velocity term, frictional loss term, dependent on velocity. Write ourselves a new equation using velocity is equal to dx dt, that's the velocity in the x direction. Solutions take this form now. You get this exponential factor. Notice it's a negative exponential. That means it's going to decay. So if you start really big, eventually it'll go and flatline. And then your angular frequency becomes your original angular frequency with just this new piece right here, this omega squared. Well, this is omega squared. This piece over here is your frictional loss. Final point, probably one of the coolest results in all of physics. Oscillations of any system around a stable equilibrium can be modeled as a spring. So we use the Taylor series. How do we know this? Well, if it's equilibrium, here's your first derivative. That's 0. Whoops. And then we have to think, because that's f prime. And then we know it's concave up because it's a stable equilibrium. So all we have is this term This term, term squared, looks like a spring. We like to think of a lot of things as springs. It's kind of fun. Now, I know your mind's reeling because you just found out that you can model any small oscillation of any equilibrium point as a spring, but let's move on to a couple examples. So the period for one oscillation of the disk. So this disk is going to rotate as it goes. That's why it has some rotational. Start with the energy equation, just like we always do. Take the derivative. Oh, again, this is the I for a disk. And this right here is omega equals V over R. This relationship, getting all your variables to match, very important. All right, dE equals 0 because isolated system. Good. MAX, 1/2 MAX. Again, we related those two terms. Here's your effective oscillation, or your effective spring constant, my mistake. And then you get your A right here, where this is your mass effective, and this right here is your K effective. So then you know that your period is 2 pi over omega. Well, these are just numbers now, so put these numbers in here, and that's the time it takes to complete one oscillation. Second example. Now what we're looking at here, we just attached the spring down here. Okay, so now we're adding this spring energy to our minus mg cosine theta like we had before. Write the energy equation. Take the derivative, isolated system, so it's equal to 0. Oh, no, I get this weird piece. What are we going to do with that? Well, tell you what we're going to do. We are going to Taylor series, where if you expand sine theta from before, if you just look at the first term, sine theta becomes theta, approximately, in small oscillations. That was the very key point. And cosine theta is approximately 1 for small oscillations. That's Taylor series. Again, you use series to make your life so much easier. With our new approximations, we plug those in and get your angular frequency of the system. I hope that helps. I hope you see the importance of Taylor series expansions. And please ask if you have any questions. I will see you in class.